And now we're getting into the meat of the day. I'm privileged to present John Hawthorn as today's keynote speaker. I first met John almost 5 years ago to the day in Minneapolis at RailsConf 2019. I was basically a newcomer to the community, and I was just meeting lots of interesting people. I was talking to Matthew Draper, who was working on gel, and I was asking about like how he got gel to work so fast, and he said, "Oh, John is the brains behind the algorithm that's behind this tool, which is called PubGrub. The algorithm doesn't belong to John, but he is the one who ported it and wrote it in Ruby. And it's a dependency resolution algorithm, and that was the first time I heard of it. I was really impressed, and the more I talked to John, the more I was impressed by his intellect and curiosity. Later on, that PubGrub gem started to be used by Bundler. So today, Bundler's dependency resolution is using that PubGrub algorithm and the gem that was originally written by John. So John is, in that way, kind of everywhere, but we don't really see his work day in, day out, because he's quite behind the scenes. He's also one of the 3 people in the world who are both Rails core and Ruby core members, which is a great privilege. And he's a staff engineer at GitHub. So with all that said, it's my pride and privilege to invite John to the stage.
Thanks. This talks about Ruby and Rails performance, which is what I spend most of my time working on. I don't think we always appreciate just how different performance is from the typical feature work we're doing day to day. Normally, when we're doing development, we're looking for a specific outcome. And something like our tests pass, or the page renders and displays the way it should with the right data. And once you achieve that output, you're done, or at least until someone changes requirements. Performance, on the other hand, is quite different. It's about this continuous number, the time something took to do. And it's something we'd like to be lower. This has 2 implications. First, you can measure improvements to this objectively. If you make something 10% faster, that's just objectively 10% better. But second is you're never done. You could keep trying to lower these numbers forever, and you'll get diminishing returns, but you can keep working on it. I think performance work, however, is not just about that number as a result. It's also about learning about your program. In other words, when talking about performance, it's not the destination, it's the journey. And I can think of no better example of performance teaching you about your program than the recent backdoor in the XZC library. This was discovered by a Postgres developer who's doing full system profiling, and just discovered that, wow, OpenSSH is doing wild things it should not be doing. And it would be a stretch for me to suggest that working on performance will make your application more secure, but it will help you better understand it and show you things that it shouldn't be doing or are taking more time than we think they should. I think Ruby and Rails get unfairly treated often when we talk about performance. Rails is an excellent framework for scaling up. Especially more recent versions have features like multi-database and sharding support, which are things you aren't going to need when you start out your application, but they're available for you once you grow into it. And Ruby's gotten much, much faster over the past decade. And I think a lot of folks have mental models which are still based on Ruby 1.8, which was essentially a totally different virtual machine. And now that Ruby has a JIT compiler, that math has really shifted. So I think people need to update their mental models of just how fast this language can be. However, I think there is a grain of truth to this idea people have, in that Ruby and Rails have a philosophy of not making it hard to write slow code. Ruby and Rails make it easy to do work. And by do work, I mean both get your job done, finish whatever your immediate task is, but also make work that keeps the computer busy. For example, Ruby will let you write code like this, where the mere difference of a couple characters makes for a quite expensive operation. On each iteration of this loop, we allocate 2 arrays, one of which we have to copy all the items into it, and it's just like a couple characters that makes all that happen. Other languages would shy away from exposing us to such powerful tools. And Ruby, you can write this much faster. There's a much faster spelling where you just do shoveling and call .unique bang. But, and that would lead some to think that, well, we should make Rubocop rules or have something else that prevents us from writing code. Or that when we write Ruby, we always have to be super, super careful to not write a less efficient version. And I don't think that's the case. I think it's virtuous that Ruby allows us to express code how we want, even if it's slow. Because to do otherwise would be a premature optimization. I'm sure everyone has heard the quote surrounding this, that it's the root of all evil. That's always seemed like a little strong to me. Didn't always totally buy in to that idea until I read the quote in full, which spoke to me a bit more. So this comes from Donald Knuth. It's from a paper he wrote about go-to statements, if that helps date it a little bit. He's in favor of go-to statements. So he writes, programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs. These attempts actually have a strong negative impact when debugging and maintenance are concerned. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. So this quote's not about never optimize things. It's about focusing your efforts. Remember, we can spend unlimited time improving the performance of something, so we shouldn't worry about it for the code we're not running very often, code that isn't hot. We really want to save as much time as we can when writing most code and keeping it clean, efficient, maintainable, easily replaceable, so that we can make that 3% of our code, or some small amount, as fast as possible. We can allocate all of our time there. So that's great. The problem is it's very hard to know what's slow, like really, really hard. I spend most of my time working on performance, and somehow I'm still terrible at guessing what actually is taking time on a given page. And I have a theory as to why. We tend to expect that the time something takes is aligned with how useful it is or how important it is to the end result. But often, that's the best opportunity we have to improve things, is when there's a mismatch, when something is taking a long time but isn't particularly useful. We heard in Nadia's opening keynote about how she had a slow query in StoryGraph that was causing performance problems, but wasn't actually used at all on the page. So you'd never expect visiting the page that, oh, it was running a query that wasn't doing anything, because you saw no effect of that. And that's the ideal case, that you can just delete something. That's always faster. So we humans are not great at this, and we need a tool to help to find out where we should be spending our optimization efforts. And today I'd like to introduce you to Vernier, a new Ruby open source profiler for Ruby 3.2+ that helps show you where your program is spending time and to better understand it. I'm going to start out with a quick demo. So Vernier comes with a CLI to easily measure a command. We're going to measure bundle update with a mostly empty gem file. I think I have just rack in here. So we can run that, wait for it to finish, and it will tell us that it recorded a result and where that file went. And this took about 0.6 seconds to run, which is that's not slow. I just picked this as an example because Bundler is an easy way we can all get non-trivial work done. It's a good test project. So we have this file. Next, we need a tool to view this. And that's the second component of Vernier, a single page web app. You can find this at vernier.prof. This is actually, if you'd like to follow along, this is the bundler example. And this web viewer was the original driving force behind writing a new Ruby profiler. It's a really great tool, and it has a really sophisticated and powerful way to look at these profiles. And I'm comfortable singing its praises because I did not write it. This is just a light skin over the Firefox profiler front end. Mostly, we've just gone through it and swapped out the word JavaScript for Ruby. And that might sound a bit strange, but the Firefox team did actually write this viewer with other tools targeting it in mind. So they did want it to be used in this way. But also, these projects aren't quite as different as you might think. They're both C or C++ applications, which are multi-threaded, have a JIT compiler to run a dynamic language. So many of the things they found they needed when profiling Firefox, both as web developers and as developers of Firefox himself, are going to be useful tools for us as Ruby developers. So once we drag that in, this is what we're going to see at first. We'll see a timeline displayed at the top that shows a chronological representation of what your program's doing at each point in time. We can mouse over, and it'll show us the stack at each point. And this is just millisecond by millisecond, what was running on bundle update. If we'd done a puts caller or raise an exception, that's showing us the same thing that would have been output. The lower part of the screen shows the exact same thing. It's just in a slightly different form where we've layered the stacks on top of each other. And these are just visualizations to help us find things in this. Now, this is, I find these can be very intimidating and hard to read. And that's sort of by design. The idea behind this sort of flame graph or stack chart style view is that we're really good at noticing visual patterns. So this is just presenting us as much data as possible in just throwing it at the screen and trusting that we'll probably be able to parse out what's happening. So if this seems like too much data, or you've ever opened one of these and you're like, that's a lot, that's totally normal. Just be patient, trust yourself on this. But there's easier options. There's also a call tree view, which is gives us more of a summary. A top style list, which tells us which method we spent the most time in. And initially what it tells us is not very useful. It's saying that main is taking 100% of time, which, okay, I could have guessed that one. So this is the more top-down or bottom-up. I never know which direction is which, but we can click on invert call stack, and it will show us the more helpful direction. And here now it's actually showing us some stuff that's interesting. So we're starting up Bundler, so we're seeing some requires. We're seeing TCP sockets, so we must be doing some network I/O. But the top method here is pretty interesting. String split. Now, string split is a C function, so is C slow? Probably not. In fact, I don't think string split is slow. It's probably doing what it's doing about as fast as it can. Why it's here is that we're either giving it a very large input or we're calling it lots of times. So we can expand that and see who's calling that. And here we see 2 lines inside of bundler that we're calling into string split. Bundler, both inside bundler, compact index client, cache. The first one looks like it's taking the majority of the time. So to explore what this is doing, we can double click it. Another feature of the Vernier front end we've done on top of Firefox is that any public gems you can view the source code of inside of this viewer. And I think this should be really helpful as a way to get involved in the libraries, the framework you're using, because we imagine there's this separation between whatever application you ship and the framework and libraries you're using. But to the computer, and when you're looking at performance, there's really no difference. So don't be afraid to look into what the libraries you're using are doing. And so this has some annotation in the margin to show the relative performance of these. These are measured in samples. We don't have to worry about that too much right now. But we can just let's take a closer look at these 2 lines. So what this is doing is it's taking a string that's a line, splitting it by spaces, assigning that into variables, and then doing a hash assignment with those variables. And there's nothing particularly wrong with this, but this happens to run 200,000 times, which is, quite a lot. And each time the work it's doing, it's the strings that come in. I looked into what this is. We're downloading a file from the internet that has a list of every single gem, and then a bunch of numbers, and then a checksum. And we're splitting it into these separate variables, or into 3 separate strings, and then wrapping that in an array to return it. Here I can show Vernier's first new feature compared to other profilers, which is that in addition to timing data, we also sample allocation data. So we can switch to that. Other profilers have been able to record allocation data, but Vernier is the first Ruby profiler, to my knowledge, to have both in the same profile. And I really want the profiles we generate to be a single artifact representing everything we can know about a program's run. That way we don't have to do so much back and forth where you make a profile, you measure things, you realize it didn't have all the information, and you have to repeat. And so we see here that this is we're running it 200,000 times, and it's making 890,000 allocations. That's quite a lot. So let's see what we can try to do about that. And if I knew bundler better, or there might be other options we could do, like running this less time would be the best choice. But another way we could do this, without knowing too much, is to just try to avoid that array allocation and that middle string allocation. Just do a substring, get them out by substring operations instead of a string split. So we can make that change, see how it does. Before, this was taking about 0.6 seconds. And then with making that change, it's about 0.5 seconds. So saving 100 milliseconds. This is why I find performance work so addictive. We can make an improvement to bundler without really having any deep knowledge of how it works going in. In fact, we've only gained knowledge by doing this. We now know that this compact index is probably an important part of bundler, and we could probably learn more and get involved in the project from that knowledge. I want to point out one thing I didn't do here. I did not use a profiler to measure the improvement. Profilers can introduce overhead and just kind of mess up the results so doing a timing on its own is always the best way to do this, to make sure that you've actually made an improvement and not just tricked your profiler into not measuring the thing that could be slow. The other thing is, please keep using string split. String split is not slow. It's just, if you call it with expensive things, it's slow. These are all of the string splits inside of just bundler that we assign into variables, and none of the others showed up on our profile, so they're probably all fine. In fact, I'm not even sure the example I gave is worth committing. That might itself be a premature optimization, and we might be fine with the time it takes, or there might be better ways to improve that if we actually decide we need to. So what I've shown you can do with any Ruby profiler. StackProf, RBSpy, or Vernier are all great options. So if you're not yet on Ruby 3.2 plus, please feel free to use one of the others. Don't wait until you have it. I think using any profiler is great. But I think Vernier has advanced the way we can use a profiler in Ruby quite a bit. So I'm going to back up a whole bunch and explain why measuring things can be more challenging than it seems. So if we have a piece of code we want to measure, how do we do that? Well, you might write something like this. I write things like this all the time, where you just take a time before, you take a time after, and then print out the difference between the two. This totally works fine, but there's some improvements we can make on it. The first is that time.now isn't always the best choice, and instead you should be using clock get time with clock monotonic. So the operating system gives us a variety of clocks that we can use to measure things. The first is the real-time clock. It's the human clock we use that says it's 9:37 a.m. But that can have some problems for timing because that needs to get adjusted and synchronized, and I don't know how it deals with leap seconds. It has weird things so that it makes sense to us. The monotonic time, on the other hand, is a time that is more consistent. It never gets adjusted. I think of this, I'm pretty sure what it is the number of seconds since your computer's booted. So you can't share it between servers, but if you want to time something just on your machine, that's the best choice. There's also CPU time clocks, and I think those are less like clocks and more like a car's odometer. Hopefully the car analogy is fitting for Detroit. So CPU time, this only counts up when your program's actually running. If you're waiting on I/O or waiting on a network or sleeping or on a lock or anything of that nature, it's not going to count up. It's just going to stay at the current time until you start running code again. And profilers are split on which style of timing to use, wall time or CPU time. And there's sometimes you might like to use CPU time. Maybe that's the resource you're out of. But I think, personally, I always prefer wall time, so that's what Vernier uses. If we're spending most of our time doing I/O or waiting for the database, I would like to know about that. That's the thing I'd rather focus on. So we'll use monotonic, and this timing is great. The next problem we run into is that you probably don't want to just litter your source code with print statements for timing. I mean, I do this, you just have to get rid of them before committing. But sometimes you have things you might want to time over a longer period of time or come back to and make sure they're not exceeding expectations, or maybe you have stats_d or some type of metrics you're sending to. So a good tool to help with this is active support notifications. This is an instrumentation framework that's built into Rails. Rails uses this to time all sorts of things within itself. And you can use your own topics too. And I would encourage doing it. It's a very good tool. And then after instrumenting, you can have elsewhere, you can write subscribers, which get a callback every time that event happens, and it will tell you about the time it took. I would advise caution with the subscribers. There is some cost to adding them. It's not too bad, but the real danger is you probably don't want to put very expensive work into here, because if you end up doing something like running a query every time you run a query, that will end badly. And you're probably already familiar with active support notifications, at least indirectly, because they're what powers the Rails logging. Anytime you've seen this printed out in your development console, select statements, action view renders, that's all coming through active support notifications. And then there's a subscriber that prints it out to the log. So the first innovation Vernier has is that we also collect all of these Rails subscribers and just log them into the profile. So again, the artifact gets to include more information. Looking at these linearly, though, can be a bit misleading. If we were to just sum up, either on purpose or just mentally, the different numbers from these, we might expect that to tell us about the time in total that these took. What is this? 14 milliseconds? But in reality, that's not actually how this program ran. If we look at it on a time scale, we actually had an 8 millisecond thing that just had a bunch of slower things inside it. So this is just a gotcha to look out for, that the total time something took, you can't necessarily sum up all of them. They may be nesting other things inside them. So using a timeline view, I think, helps a lot with this. And I found this very useful, and I think this will be very helpful. And for many projects, this might be enough for you. Like, you might not need to go all the way to profiling. Often, just making sure all your queries are fast enough for simple projects is likely enough. We're also able to include some other markers. Vernier subscribes to a few Ruby internal APIs, or APIs exposed to C, which gives it more information about what the VM is doing. For example, we have instrumentation of the garbage collector, so you can see where the garbage collector is when the garbage collector is active. I think the garbage collector has been another place folks have prematurely worried about performance. Anytime Ruby seems slow, it feels like, well, it's a garbage collected language, of course it's slow. But in reality, Ruby's GC can be quite sophisticated. And here we see that the sweeping it's doing is actually incremental. It's just taking tiny slivers of time to do that marking. And your program's able to run between all of those. The weakness, of course, of the markers notification style is that we need to know about them in advance. We're only recording things that people have thought about. This is probably slow, and we should write about it. It also only works for things that are targeting Rails. So if you use a library that doesn't integrate, then that won't help you out. So profiling solves that. And the way you might think of profiling, in the simplest way to do it, would be to just instrument every single method that's ever called in your system. And that's a technique that does totally work for profiling. It's called a tracing profiler. You could use an API like Ruby's tracepoint to get a callback every time you enter a method call, and then have another callback at the return. And then we can just take the difference in times again. The problem with this technique is that it can be a little slow. So, for example, with this recursive Fibonacci script I tried, running it without any profiling takes 0.1 second. But if we use profile.rb, which is the original profiler which at least used to ship with Ruby, it would end up 500 times slower. So way, way slower. And maybe that makes sense. Like, if for every line of Ruby we have to run several more lines of Ruby in order to instrument that, that's going to add up. But even if we use something written in C, this is the same way RubyProf works, even that's 30 times slower. And there's a couple big problems with that. For one, something that's 30 times slower is probably too slow to ever run in production. And oh yeah, this also is not compatible with a JIT compiler, so it's probably even more than 30 times slower today. Yeah, so this is not compatible with production, and really you should be aiming to do profiling in production if you're able to. Production, like real production servers, are the only way the latencies are going to be the ones you should actually be measuring and the real problems you're seeing. But if you can't do that, Rails in production, often that's good enough. But it's important that development can be quite different. So the closer to production you can get while profiling, the better. The other problem is that when something is 28 times slower, we're not measuring the same program. That's going to affect the results we get from the timing. And worse than that, this doesn't slow down the program in a consistent way. So a Ruby program's a mix of things. Some of the time is spent executing Ruby code. Other time is spent inside of native code, like a C function usually, something like string.split we saw earlier. And then other time is spent idle. But if we are slowing down specifically the Ruby code, we're not going to be measuring the real program. We're going to be measuring a program where Ruby is 30 times slower than it should be. And that could mislead you into trying to optimize the wrong thing or making the wrong trade-off. So I'm not a big fan of the tracing profiler technique. It does have one really great feature, which is that it tells you how many times a method was called, which the other technique can't do. But if we're concerned about measuring timing accurately, we instead want to use a sampling profiler. So a sampling profiler works by having a loop where it has an interval where we do something every so often, which could be called the interval or the sampling rate. And then every so often, what we want to do is take a sample. So in this case, we're grabbing a backtrace from the main thread and saving it into an array. So as our program runs, we'll collect these samples, which are, again, as if we'd looked at caller or raised an exception at that point in time. And this is what can power these stack chart style views. And again, these take some interpretation, look at them from a distance. You'll see that they do resemble, they are the same shape as the markers we had. It's just that they give much more detail. And we can mouse over them, double-click them, see lots of data in this. Again, this is a great way to get more familiar with the internals of a framework. Things like active records, making a query, is one of the hardest things to parse out from just reading code. But when you run this in a profiler, it shows you the order that all of these things are run. And I think that can really help out. So this is a really good mental model of how a sampling profiler works. Just sleeping and recording backtraces, and then doing some statistics at the end of that to show you a result. And I think this helps understand a lot of the quirks this type of profiler has. If you call a method and it's super fast and you only call it one time, a sampling profiler probably won't tell you about it. It also, you'll notice you can't differentiate method calls starting and ending. It's sort of just, you just sort of have to guess. And this sampling profiler is a little better than pseudocode. I've tested this out, and it does actually work. But it's surprisingly hard to make this technique as accurate as we might want. So if we want to measure something like, if we measure a program that's totally idle, this pure Ruby profiler works great. It sleeps for a millisecond, takes a sample, and it repeats until it's done. Well, with this, we'll properly capture 1,000 samples sleeping. But if we measure something a little more complicated, or I guess in this case, intentionally bad, so here I have a program which also takes 1 second to run, but instead of sleeping, it just loops until 1 whole second has passed. And if we try to profile this with our pure Ruby profiler, we won't get those 1,000 samples. We'll get, I think I got 20 when I tested this. And that's because we run into GVL contention. Ruby has a global lock, the global VM lock, which only allows one thread to run at a time. Or, sorry, it only allows one thread to execute Ruby code at a time. That might sound worse than it is. We can still do I/O in parallel. We can still do some C functions in parallel. It's just Ruby execution, which can be a problem. And I think this is something also that people have had premature worries about it being a problem. And I worry that we've often avoided using threads in cases they'd be very great choices for us, just because we don't know whether or not the GVL will be an issue. So one thing we've also got Vernier to subscribe to from Ruby is a new API that came in Ruby 3.2 that shows you the state of the GVL. We get a callback every time the GVL is acquired or released from a given thread, and we also report that in a marker chart. So now you can confidently use threads and see where they do or don't work. And this is a bit odd, but I'm using Vernier to profile our pure Ruby profiler, profiling the code. Hopefully that makes sense. But here we can see that, yes, that was our problem. Our thread ended up stalled where it was not able to run and record the backtraces we wanted it to. So we represent the GVL in 3 different states. It's either running, holding the GVL, executing Ruby code. It's stalled. It's blocked acquiring the GVL because some other thread is running. Or the thread is suspended. It's released the GVL to do I/O, network, whatever. The suspended state accidentally, I think, became one of the best features of Vernier. Because in addition to recording that we were suspended, we started recording the stack at the time we were suspended. So if you're using a well-behaved library, we actually end up with a marker added every time your program does I/O, just automatically, because you should be releasing the GVL to do I/O. So here we can see inside of Bundler, where it was opening that TCP socket to do the network request, even though it didn't have its own instrumentation. It's kind of a nice fallback we have. OK, so a pure Ruby profiler, not surprising that didn't work. We sort of had the same problem with profile RB. It's kind of hard to measure Ruby with itself. So there are much better choices, like StackProf. StackProf's a really good profiler. It's probably the profiler I've used the most, and it's the profiler I used and worked on before starting Vernier. And instead of running a thread or doing anything in Ruby, it works using, it's a C library, and it works by using Unix signals. So a Unix signal, it configures Unix signals to call or to wake itself up every so often. And Unix signals are very, very strange in that they interrupt your program in the middle of execution at any point. So because of that, it's unsafe to do much of anything inside of a signal handler. So all StackProf's able to do is to queue a job using this Ruby API that is then run at a point the VM decides that it's safe. It's finished doing allocations or things, and the stack's in a consistent state. And it's safe to allocate again and make a profile. So we queue up a job, then we wait to a safe point, and then StackProf is able to record the frames and save the sample. And this works fairly well. It does great with the weird sleeping loop we had before, but it has its own problems. So here's an example program I've made where we have an empty method and a slow method. The slow method does a bunch of string operations just to waste time, and then calls into the empty method. So we'd expect from this that our slow method would be blamed for most of the time, and our empty method is probably quick if we spend any time in there at all. The problem is the safe points in this program only occur at the return from empty method and the return from slow method. So if we are to profile this, we actually blame 100% of the time on empty method. And I've wasted days on things I was convinced were slow, but in fact were just seeing this problem. And I've since learned this is a problem other languages have had too. I think the JVM also has this safe point bias problem. So a couple years back, I tried fixing this in StackProf, or I did fix this in StackProf by taking the frame collecting and moving it into the Unix signal, and then only doing the saving of the sample at the save point. And this helped a lot. This removed the bias, but it still had some issues. If instead, if we never get to a save point, or if a save point doesn't occur between two of the samples we were hoping to collect, we will just replace the buffer, and we'll end up missing a sample. And this ended up not too uncommon. And it might happen more often if there's a misbehaving C library that is holding the GVL and should be releasing it but doesn't. And you could argue that we should just fix those C extensions. But the problem is a profiler is really the thing I'd like to be able to tell me about the C extensions I need to fix. And also, it should just work. So this is the first thing Vernier is able to completely fix. We reintroduce a thread, but this time it's not a Ruby thread, it's a C thread. And the only responsibility for this thread is to save the samples which are queued up by the running program. So because of this, Vernier, as long as your computer is fast enough, will never miss a sample, and it will have no bias to those samples. It will just be able to record every sample that it sees. So because of that, it's more accurate. It's also lower overhead. Previously, we had to do the work of saving the sample inside of the main thread, and that would slow down the program slightly. By moving that into a dedicated C thread, we save time there as well. Another improvement we made to StackProf in the past was, again, Unix signals they're so strange. So they arrive on an arbitrary thread, and I guess arbitrary usually means the main thread. So for a long time, if you tried to record a profile on a web server like Puma, which is multi-threaded, it would only profile the main thread, which doesn't do anything. The main thread just waits for the other threads, which actually do the work. So if you tried doing some profiling, say, 2 or 3 years ago and found that it just didn't work, please try again. And it was not your fault, it was ours, so sorry. We improved that a while back, but in a sort of unsatisfying way. We ended up just forwarding signals to whichever thread the profile was started on. And that helped a lot, and it worked for the style of profiling where you have a middleware that profiles the request that's coming in. But I think it gave an incomplete view, because that doesn't really help a lot if you want to profile Sidekick or some sort of threaded job worker. And also it meant that you couldn't really see what was happening if you spawned any threads within your web request, or if 2 web requests were being served at the same time. So one of our early goals for Vernier was to be able to profile every running thread. And initially, we just implemented that very naively, where we just ask every single thread what it was doing at every sample rate, and then record all of that data. And this did work, but there was some worry with this that would add a lot of overhead, and it would add overhead related to how many threads you had, which it would be very disappointing if my writing this profiler this way discouraged people from using threads to their full potential. But eventually, we realized that there was a trick we could use, and we don't actually have to look at all the threads. Because we subscribe to the GVL API, we actually know which threads are running and which threads are idle. And because idle threads aren't allowed to execute Ruby code, we know that their stack trace isn't changing. Only the thread which holds the GVL is able to change, and that's only 1 thread per ractor. So we're able to capture a sample from every single thread throughout the entire program's execution with no extra overhead, giving us a totally full view of the whole program running. So I've recently moved from the Ruby Social Mastodon instance to my own self-hosted Mastodon server. A couple of reasons for this. I'd like to say it was for, I don't know, owning my own social media presence or something like that, but truthfully, it's more I wanted to buy another domain name. But also, I needed a good test app to profile, and Mastodon's a very interesting application for this. Mastodon's a fairly normal Ruby and Rails application. I think it's a quite well written one. And it has lots of non-Rails developers who have an interest in self-hosting it. And it's been interesting to see them rediscover the same things we have about how do you tune a sidekick worker, how many threads, how many workers, how many processes do you need for that to run effectively. But they've had to treat it somewhat as a black box, not knowing Ruby or Rails as well as we might. But we've also, I think, many ways before having a profiler that can look at everything, also been treating it as a black box. So here's the way I think we can now profile programs in a way that previous profilers have not been able to. We can start our web server configured so that sending in a signal will start and stop a profile. And then we can SSH in and send that signal. So I ran this on my Mastodon instance when loading the home page and captured a profile something like this. So this shows all the threads which are running, all the Puma threads which are running on my Mastodon server for a 3-second period, and a whole bunch of requests came in at the same time. And we can do traditional work with this, where we zoom in on one specific request and then do the traditional profiling we might hear. I think there's an N+1 in here that I found that I will try to fix. But we can also see things that before would have been a mystery as to why a certain request was slower than it should have been. Later in here, we have a request where I guess we were serving more requests than we were able to. I'm only running with a single process because I intentionally want this to happen. But we see that this request spent some of its time stalled. So we actually were not able to serve it as fast as we could, but this request wasn't actually to blame for it. And now we can see that actually it was another request which was in the running state that was holding the GVL for a long time. And if we wanted to serve our other requests faster, we now know that this is the area we need to improve on. So this is my hope for Vernier, that we're able to capture a moment or several moments in time from a running Ruby process with as much detail as we possibly can get. I hope this has convinced you to try a profiler. Using a profiler lets you write Ruby confidently without worrying about the minor inefficiencies. In addition to improving your application's performance, I can guarantee you'll learn about your application, about Rails, and about the gems you use. And this might be cheesy, but lately when I've seen slow things in profiles, I've been trying not to look at them as performance problems, but as performance opportunities. When you find something that's taking time, there's two possibilities. It's either doing the work you've asked it to in about the most efficient way you can, or it's an opportunity to improve whatever you've called. If something's slow in the library, framework, or even language you use, it can be a good chance to get involved upstream. And we'll have a stronger, better community, and you'll have a faster application as a result. Thank you.